Hi, my name is Antonio Cervantes. I'm a mechanical engineering grad student working on a personal project called the DonkeyCar project. So what is DonkeyCar? DonkeyCar is an open source self-driving car platform for small scale vehicles. DonkeyCar makes use of artificial intelligence neural networks to train autopilots to drive RC cars via a camera as its main sensor. DonkeyCar is also a great platform for creating and testing new ideas for self-driving cars in a safe manner because the vehicle's small size and open source code makes it easy to add new parts for research and development. So why did I want to start working on this project? Well, I've always had a passion for cars and more recently found a passion for robotics as well. So what better way to combine the two than by making a self-driving car, especially at the small scale where it's safe enough to crash and also easy enough to reiterate. To get this project started, you first need an RC car. I'm using the Arma Typhoon 1/8 scale, which is a very fast car with a max speed of 30 miles per hour. You can technically use any RC car as long as it has proper access to the servo motor for steering and electronic speed controller for throttle. Next, you need a wide-angle camera. This is the only sensor needed to get the car up and running. The camera is used for visual perception of the racetrack, and its data is fed directly to the neural network for decision making. I'm using a CSI camera with the 160-degree viewing lens. Next is the single board computer for onboard processing. I'm using the Jetson Nano for its high-powered GPU, but you can also use the Raspberry Pi as well. After that is the wireless connectivity. The main communication type is Wi-Fi, and it's used for communication between the Jetson Nano and the host PC. Next is the PCA 9685. This is a PWM driver board which connects to and controls the servo motor and ESC. You also need a battery bank to power the single board computer. I opted for a solar powered battery bank, which helped out a lot with prolonging the battery life, especially when sunlight came through my garage window, which is where I had my test track. Finally, you need a gamepad and host PC. The gamepad is a remote control used for manually driving the car to collect data. I'm using the Xbox controller, but you can also use a PS4 controller or a RC car controller. The host PC is used for remote operation of the car and for running machine learning training algorithms, which can be computationally heavy and too much for the single board computer to handle. Going over the schematic for DonkeyCar components, the parts can be broken up into two sections. The area in the red box is what you would add on to the car for its self-driving, and the area in the blue box is what comes stock with the RC car. Looking at the DonkeyCar add-ons, we have the gamepad, which can be connected directly to the host PC or wirelessly to the Jetson Nano. The gamepad is set up this way so the control inputs can be recorded for the Jetson Nano for training. Next, we have the host PC. This communicates back and forth wirelessly to the Jetson Nano over Wi-Fi. Then we have the Jetson Nano. This takes data from the camera and inputs it into a neural network to produce steering and throttle values. These values are passed to the PCA 9685, which produces PWM signals for the servo and electronic speed controller. So the steps taken to train the DonkeyCar can be seen in the following flowchart. First, you would start by manually driving the DonkeyCar. This is where you would use the remote controller to drive the DonkeyCar on the racetrack. The software would automatically record your driving inputs as well as taking photos. Then that data gets saved onto the Jetson Nano. After that, that data is then transferred to the host PC for processing. The host PC runs the training software and builds a model from that. After that, you transfer that model to the Jetson Nano. And finally, you run autopilot with the built model. So in my initial test runs, I'm using the full TensorFlow model versions. So these are the larger files for TensorFlow modeling. And using those on a smaller computer board led to slow reaction times and just slow inferencing for the neural network. And so you can see the car has pretty much a slow reaction time. So in this next test, I'm using the TensorFlow Lite model. And this is a lighter version of the TensorFlow modeling, which actually allows for faster inferencing on a small computer board. This gave the car much faster and better control of steering. However, it was only able to drive around the track for 1.5 laps due to a sort of a bad control of the throttling. It seemed to go too fast into the corners. You can see that the car is dragging around and crashing into the cones. The cones are added as a way for the AI to help see when it goes into a corner. But most likely in my next revisions, I'll take those out. So next, I opted to use local angle, which gives me control of the throttle and the Jetson Nano control of the steering. And this actually opted for the best results of the car. What I did was I basically slowed down as the car went into the corners. For future updates, I'm gonna have to fix how the car controls its steering because it seems to go too fast into corners. But using local angle and giving control of throttle to myself allowed the car to go around the track very many times. So you can see in the speed up, the car makes it smoothly around the track, doesn't crash into any cones, and just repeats a lot of laps around the track. So then here you'll start to see that there's sort of an issue with my ESC. I think it's due to an overheating problem, but essentially it starts to lose power after driving for so long. So some key takeaways to this project is the current linear model doesn't have great control over throttle. For some reason, it seems to either go too fast or too slow into corners. Also, adding cones onto the racetrack helps, but it's not really needed if you have good lane lines laid down on the floor. For future updates, I plan to build a better model type for faster inferencing or reaction time. So I'm thinking of looking into maybe the TensorRT models or something else. I also want to fix the local pilot's throttle control issue. I want the car to be able to have good control going into corners, but not to go too fast into corners and basically spin out. I also want to fix my ESC's overheating issue. I'll most likely add a fan or something to cool down the ESC so that it can drive for longer times on the track. Next, I want to implement an IMU. I just want to add more sensors to the neural network to help it, just to see if it improves drive performance or better handling overall. I also want to implement an RP LiDAR for obstacle avoidance and possibly to help localize and navigate around the track. And finally, I want to build a track with more complex turns. As you saw in the test videos, my track was just an oval shaped track. I want to add some more left turns, right turns, maybe some chicanes or something that can add a bit of complexity and just to really test how much the AI can handle. So thank you for watching this video. I hope you really enjoyed. The DonkeyCar project is a really fun project, and I can see it as like a really great way to learn machine learning, artificial intelligence, autonomous robotics. There's so much to learn from this, and I really encourage anyone interested to give it a try. Thank you.